Sometimes you don't need to do an entire vibrational analysis of your entire molecule with the XYZ coordinates on every atom. It might get very complicated. So in some cases, if we're only interested in one vibration of interest, we can just look at that mode by itself. And so let's give an example. So what we're going to talk about today are metal carbonyls. And so metal carbonyls have a very unique stretch for the CO vibration. So here's our CO. Here's a metal carbonyl. So this CO stretch along the CO vector. So of course there are other vibrational modes where the metal can move, the carbon can move in other directions, bending, in plane, out of plane. All we care about is this stretch, this CO stretch. And the reason is that this, again, is very unique. Often it's going to be around, I don't know, it can go between 1700 and 2100 wave number. And so this is it's very kind of by itself. So because of that, it's easy to look at. It's very distinct. It's also a very strong IR or Raman signature. So because of that, it's really useful for assigning structure. So let's give one example. So if we think about a square planar molecule, so it has two ligands here, and we know there's two carbonyls, something like this. This cis geometry molecule is actually going to have very different IR spectra compared to the trans. And so rather than having to do, let's see, 3n minus 6, so we have 1, 2, 3, 4, 5, 6, 7. That would be 15 vibrational modes to go through. What we can instead do is treat just the two CO vectors of both molecules here. And then we can then derive the CO stretching modes and then figure out what they should look like in IR spectroscopy. So let's first assign the point groups. This is C2V, and then this is D2H. And then so what we can then do is I'll just do the C2V one for now. So here's our C2V. Let's do our E. We have our C2, sigma V prime. So now if we want to look at just our gamma COs, so we have two of the CO stretches. So our group is 2. If we do a C2 about this axis, then both of the carbonyls move positions, so we get a 0. If we do a sigma V in plane of the board, they stay the same, so we get a 2. And then sigma V prime is into the board, so they switch positions. Because they move positions, again, off diagonal matrix elements, our trace is 0. So what this means is that our gamma CO is going to be equal to A1 plus B1. So you could do your projection operators, and we could know that A1 is going to be the symmetric CO stretch where they're both going out like this way, and then B1 is the anti-symmetric one where they're kind of alternating like this. So because of this, if we look at then how these transform in XYZ, both of these, I'll have you take the character table, but both of these are IR active. So if you take the IR spectrum of this molecule, you expect to see 2 CO stretching bands in the spectrum. In comparison, for this D2H molecule, I'll let you go through it on your own with the D2H character table, but for the trans isomer, our gamma CO equals AG plus B. And so because of that, the BU is not IR active. Oh, wait, sorry, excuse me. Sorry. The AG is not IR active because it's centrosymmetric. So G is Garada. So because of that, it can't transform as X, Y, or Z. So this is not IR active. But this one is IR active. And then so because of that, if you take the IR spectrum of this molecule, then you expect to see one IR active band. And then so you can distinguish these two isomers using vibrational spectroscopy. And then just as a reference, AG should be Raman active because it should transform as a square function. So we'll do another example of this in class as well.